Okay, welcome to this last session for today, the last session that will separate you and all of us from the social dinner. It is the first session of the conference on optimization and evaluation. So I would like to invite the first speaker on stage, Zexu Sun, and he will present the paper End-to-End Cost-Effective Incentive Recommendation Under Budget Constraints with Uplift Modeling. Welcome.
Hello, everyone. My name is Zexu Sun. I'm a PhD candidate from Renmin University of China. Now I'm going to introduce a work accepted by the RecSys entitled End-to-End Cost-Effective Incentive Recommendation under budget constraint with Uplift modeling. With the development of online platforms, online marketing has become increasingly essential and competitive. Assigning customers discounts or bonus is a critical strategy for promoting user conversion and increasing revenue. For instance, Taobao utilizes coupons to enhance the user activity. Booking employs promotion to improve user satisfaction. In an online marketing scenario, recommending a more significant incentive to customers can increase the purchase probability. And it's reasonable to hypothesize that an increased incentive is unlikely to change the spending behavior significantly. However, the incentive recommendation is often constrained by a limited budget, which means that only a proportion of limited budget. Which means only a part of a person can receive the incentive, that is the persuadable person in the figure. This problem is typically formulated as the budget allocation problem in an online marketing problem. Several recent studies have tackled this problem using a two-stage approach. In the first stage, causal inference methods estimate the uplift, and in the second stage, an integer programming formulation finds the optimal allocation based on the predicted uplift. However, there are still some limitations to the existing methods. Firstly, the existing causal inference methods lack the interpretability and do not conform to the domain knowledge, which may result in unreliable predictions and in the practical scenarios. As shown in the figure, the response curve of a user should be monotic and smooth. For example, customers who have used the coupons of varying values typically yield distinct transactions on revenues, with larger coupons generally resulting in higher revenues, thus without incorporating the marketing domain knowledge, which may get a wrong uplift prediction of the user, and which result in non-optimal incentive recommendation. Secondly, there is an optimality gap between the two stages, as their objectives are fundamentally different. For example, with a significantly low total budget, an effective allocation algorithm should distribute incentive solely among a small subset of users which exhibit high sensitivity to incentives. In such case, a well-trained Uplift model might exhibit a wrong marketing effectiveness, and if the model demonstrates higher precision across all users on average, but performs inadequately in the subset of users. To solve the limitation in this paper, we propose an innovative E3 IR model to solve these limitations. Our contribution can be summarized in the follows. And especially, we designed an Uplift prediction module injected with marketing domain knowledge, which can ensure the user response code is monolithic and smooth. We employ the differentiable ILP layer for the budget allocation. And we also conduct extensive experiments on a public dataset and a production dataset. And the results demonstrate the superiority of our method. Here is some preliminaries. In this work, we address the persuadable assignment, personalized assignment of the incentives on an online platform. The optimization target is to maximize the overall incremental number of customers. Let D be the observed dataset with n samples, and where each sample can be represented as xt, yc, yr. Then we can have the uplift estimation objective. And we formalize the problem by the conditional average treatment effect estimation. And then in the second stage, it's a budget allocation problem. The binary treatment budget allocation problem is to assign the binary treatment to part of the individuals to maximize the overall revenue on the platform, but requires the incremental cost that does not exceed a limit budget. Let the decision variable be the z belongs to 0 and 1. Therefore, this problem can be formulated as the integer programming problem. On the left is the binary treatment budget allocation, which can be seen as a knapsack problem. And on the left is the multi-treatment budget allocation, which is formulated as the multi-choice knapsack problem. The following is our methodology. At a high level, our E3 IR consists of two modules. The left is the uplift prediction module, and the right is the differentiable allocation module. And the first module is to predict uplift in the user cost and response. Next, the second module utilizes the predict response uplift and cost uplift to facilitate budget allocation problems through a differentiable optimization procedure. Especially, the uplift prediction module is divided into two constraints. The first is a monotonic constraint. In principle, the uplification for both tau C and tau R are achieved by using optimal modeling and data from randomized controlled trials. Here is the general uplift prediction procedure for the tau C and tau R. To ensure the monotonicity, we propose a multi-treatment effect estimation model with a monotic constraint. We implicate the model incremental effect between two adjacent treatments and obtain the predict uplift through the accumulation. And the second is the smooth constraint. Smoothness means that the model's output does not change much as the incentive level varies. We leverage RecSys regularization, and where H is the RecSys continuous is if there exists a constant C is greater than 0. And then the loss function of the uplift module can be formulated as this in this equation. The next is the second module of our work. Is the differentiable allocation module. First, we need to determine the descent direction of the gradient. After we have predicted the response uplift and the cost uplift, we aim to build a differentiable incentive recommendation layer for the end-to-end optimization, which can reduce the performance gap between the uplift prediction and the budget allocation. During the backward pass, the gradients of the subsequent layers are obtained from the ILP solver. And we build a proposition for the solver to find the descent direction of the gradient. For further detail, the proof can be seen in our paper. After we have the gradient descent direction, the first we need to update the cost uplift. To obtain a significant update for an incentive change, we computed the gradient of piecewise affine local mismatch of the function, which is defined in this function in this equation. And to up the constraints, we defined the gradient as d tau c. Note that the mapping dz to d tau c is homogeneous. Then we have the cost uplift update. Then we need to update the response update, which is another part for the uplift modeling. Ignoring the distinction between feasible and infeasible ZI, the problem of updating the cost can be addressed in several prior studies. In this part, we adapt some ILP solver techniques to update the response uplift. Let I1 and I(n) be the indices of the coordinates in the absolute value of dz. We have the following equation for dzi, and the set can be calculated by the following equation delta I. Furthermore, we can have the following proposition too. This proposition can solve the choice of basis problem. Overall, we have the following loss function for the end-to-end optimization, which is the sum of the prediction loss and the budget allocation loss. And beta is the hyperparameter to control the trade-off. Then we conduct an experiment to answer the following research questions, which mainly from 3 aspects. This is a data set that we use. We use a public data set, Hailstorm, and a production data set, which is collected from one of China's biggest short video platform. These are the baseline that we use in our work, which is common in causal inference field and budget allocation. The overall performance can be shown in these 2 tables. The first table is the binary treatment allocation problem. The second table is multi-treatment. And over E3AR achieved the best performance across diverse metrics. We can also conduct a ablation study for each part in our method to show the effectiveness of each part. Furthermore, for the budget inference, we also conduct another experiment to show the influence of the budget varies. In this paper, we formulate online marketing problem with a specific budget constraint as a predict and optimize problem. To solve it, we propose an end-to-end optimization method E3AR, which consists of 2 customized modules. And extensive experiments conducted on binary treatment and multi-treatment datasets demonstrate the superiority of our method across various metrics. That's all. Thank you.
Let's thanks the speaker. I have a curiosity, if there are questions from the audience. No, the curiosity is about the 2 data sets that you have used. Which is the cost or the budget in the 2 data sets that you have used for the experiments? Which, from the practical point of view, which was the cost or the budget allocated to the 2 data sets used in the experiment?
The budget that we use in our data set is coming from the knowledge from the partner, the company partner of our work. And in the public data set, we just set the limited budget as a constraint, which is not from the data set, but we set it as a constraint in the by refer to the response in the data set, such as one person may click this item or others. It may convert as a $1 budget cost, and then we set the overall budget as a constraint which is not exist the total budget in our data set. And we, from the production data set, we set some, we get some knowledge from the company workers with us, and we set budget.
So thanks again for your presentation. And